systems of equations using algebra. The first method, and again, we're going to go through about 2 or 3 lessons from Algebra 1 in 25 to 30 minutes right now. So it's going to be a very quick recap and review of what you learned over, multiple lessons back in Algebra 1. And I'm planning on moving quick, but again, if you need me to slow down at any point during this, please let me know. In looking through this, I'm pretty sure that every single thing in here is familiar. Yesterday, most things were familiar with a little bit in terms of like, what kind of system was it? Consistent or inconsistent? Was it independent or dependent? Those were probably new. I don't think there's anything new today. So one algebraic method to solve a system of equations is a process called substitution, in which one equation is solved for one variable in terms of the other. So basically, you get an equation equal to a variable. It doesn't matter which one, first of all. So step 1, when necessary, solve at least one equation for one of the variables. Basically, get x or y by itself on one of the 2 equations. Oftentimes, there will be easier variables to get by itself than others. And so usually it'll be pretty clear which one's going to be the easiest one to get by itself. Once you have that, you're going to take what that variable is equal to and substitute it in to the other equation. That's step 2. And then once you have done that, you're going to solve for the remaining variable. So you're going to solve the equation for one of the variables. Once you have that variable solved for, you're then going to substitute that value into either equation and solve for the other variable. And then you write your answers in ordered pair because we're still trying to figure out where 2 lines cross on a graph. So we're looking for a point of intersection. So let's talk about this here. Step 1, here's our system. These are our 2 equations. Step 1 is to get one of these equations equal to either x or y. So we have this x, we have this y, we have this x, we have this y. We have 4 variables to choose from in terms of getting by itself. Which of those 4 appears to be the easiest one to get by itself? Which one? Which x? Second x, yeah. The x in the second equation is going to be the easiest one to get by itself. How come? Yeah, it's alone. There's no number in front of it. So all we have to do to get this x by itself is subtract 2y from both sides. That's it. There's no division after it. You just have to move over the 2y. So if you have a variable that does not have a coefficient, that's the one you should be getting by itself. That's just kind of like, it's not a rule because you could legitimately get any of these variables by themselves. However, it'll make it a lot more challenging if you figure out any other variable other than that one by itself to begin with. You'll get the same answers. It'll just make the process more challenging than it needs to be. So because the coefficient of x in equation 2 is 1, solve for x in that equation. That's going to be the most straightforward way to use substitution. If you don't already have a variable by itself, if one of the variables has a coefficient of 1, meaning there's no number in front of the variable, that's the one you should be getting by itself. So if you subtract 2y from each side, you get x equals negative 2y minus 12. All right. Now, in the second equation, x is equal to negative 2y minus 12, which means we are now going to substitute the value of x from the second equation in for the same variable on the first equation. Substitute that value into the other equation. So we're going to take, different color here. We're going to take negative 2y minus 12, and we are going to substitute that in for x on the first equation right there. And the reason why we're doing that is because this says x equals negative 2y minus 12. And since both x and y are the same values in both of these equations, because we're trying to figure out what point are x and y the same, so we're assuming that x and y are the same here. Because this x is negative 2y minus 12, this x is also negative 2y minus 12. And the whole purpose of this is if you try to solve an equation that has 2 separate variables, you can't get a numerical answer for it, which is not super helpful. We're trying to get numerical answers. And so the only way to really get a numerical answer for an equation is if there's only one variable. And so if we substitute out the x for what x is equal to from the other equation, negative 2y minus 12, the only variable that we have left here is y. There's only one variable. There aren't 2 separate variables now. So the variables are all the same, which means we can solve for y. So we're going to get rid of the parentheses by distributing. 8 times negative 2 is negative 16. 8 times negative 12 is what? Negative 96. And then the negative 96 doesn't combine with anything over here, but the negative 16 and the negative 3 can be combined to equal negative 19. So negative 19y minus 96 is equal to negative 1. Then we're going to add 96 to both sides. Negative 1 plus 96 is 95, positive 95, which should be equal to negative 5 then, right? When you divide 95 by negative 19 equals negative 5. So the y value is negative 5. Great. So we solved for one of our variables. Now we need to get x. Now, solving for the first variable is always going to take the longest because that's the part that actually uses all the substitution and all that kind of stuff. Solving for the second variable is actually a lot more straightforward. In fact, I wouldn't even recommend plugging it back into this equation here. So let's cross that off. I don't want that. Don't do that. We're trying to solve for x for our other variable, right? Well, we already got x by itself here. So we may as well just use this version of that second equation and not have to do any algebra. That'll make things a lot easier for us. So if we go with x equals negative 2y minus 12, that'll make our lives a little bit easier because then we don't have to do the algebra again that we already did. So we'll cross that off. Now we're going to say x equals negative 2 times negative 5 minus 12. What's negative 2 times negative 5? 10. What's 10 minus 12? Negative 2. So if you're using the substitution method, this last step here, I would not follow what the book is saying. I would just go with the version of the equation that you already got one variable by itself for, because then all you have to do is plug it in and do some math. You don't have to do algebra again. You just plug it in and evaluate, and you're good to go. So the y value is negative 5. The x value is negative 2, which means that those two lines cross at the point negative 2, negative 5. And that's the answer. Questions about that? It's our substitution method. We'll do another one on the next page, I believe. Yeah, we got another one here. A couple more substitution ones, actually. And then after that, we'll look at elimination, and then we'll be done with lesson 2.5. This is a quick lesson again. So here we go. Next page. Use substitution to solve the system. All right. If we look at both equations there, which equation should we get a variable by itself, and which variable in that equation should we be getting by itself? And when I say should, technically there is no should. But which one is going to be easiest to get by itself? The y in which equation? The first one. Because there's no number in front of y. There's no coefficient here. It's just 1. So the only thing you have to do to get y by itself here is add 5x. So that's going to be y equals 5x minus 3. So we take the value of y, which is equal to 5x minus 3, and we are going to substitute that in for y in the second equation. Now, in the first problem, we substituted in for x because we were able to get x by itself very easily. Here, we're substituting in for y because we're able to get y by itself very easily. So I'm just going to use the margin over here. I think we'll have enough room. So let's write it out. We're going to write the entire second equation. So 3x minus 8, but instead of y, we're replacing y with what y is equal to, which is 5x minus 3. And that equals 24. So we got 3x minus 8y. This is y. 5x minus 3 equals 24. We'll distribute the negative 8. So that'll be 3x. What's negative 8 times 5x? Negative 40x. What's negative 8 times negative 3? Positive 24 plus 24 equals 24. Now, if we subtract 24, that's going to be 0 over here. That's not a problem. 0 is a number. We can work with 0. And then 3 minus 40 is negative 37, x. What is 0 divided by anything? 0. So the x value is 0, which is fine. That just means that they intersect with an x value of 0, which means they intersect at the y-intercept. So whatever y is, is going to be the y-intercept, and that's where both equations intersect. So let's go back to this equation now. Substitute in 0 for x and solve for y. So we're going to say y equals 5 times 0 minus 3. 5 times 0 is 0. 0 minus 3 is what? -3. So y equals -3, which means that both lines have a y-intercept of -3. And that's where those two lines cross. So the solution is 0, -3. That is our substitution method. They won't always be nice whole numbers like this. And you can always check to see if you're right. You can always take x and y, both of those values, and plug them back into both of the original equations. And if you get two things that are equal on both of them, then you're good to go. And these both work. Or if you want to, you can double check by graphing. There's a lot of ways you can verify. Questions so far? All right, let's keep going. Example 2, substitution when there is not exactly one solution. Well, let's figure out what the heck that means. Which of these two equations is going to be easiest to get a variable by itself? The second one, yeah, because it already has a variable by itself. Okay, y is already by itself. Don't overthink it. If a variable is already by itself, just leave it and use it. Take what it gives you. So y is equal to 2x minus 11. So we're going to take that 2x minus 11. And that's what y is equal to here, which means that that's what y is equal to there. So we're going to substitute that in for y on the first equation. So you're going to rewrite the first equation, -5x plus 2.5 times the value of y, which is 2x minus 11. And that equals -15. If you multiply 2.5 times 2, we're distributing 2.5. What is 2.5 times 2? 5. Okay, so 5x. What's -11 times 2.5? What is it? -27.5. Okay, so the minus is already there, so we just need to write 27.5. What happens to these two like terms? Yeah, they cancel out. So that means there's no more variables. And we're left with a statement that says -27.5 equals -15 with no variables whatsoever. Is that a true statement? No. -27.5 clearly does not equal -15. There are no variables left. What does that tell us about this system? There's no solution. Yeah. This system has no solution because -27.5 equals -15 is not true. What does that tell you about those two equations on a graph? Based on what we talked about yesterday. They're parallel lines. Yeah, if a system doesn't have a solution, that means those two lines happen to be parallel. So if you were to get y by itself on this first equation, you would end up with y equals 2x. It would have the same slope, but it would not have -11 for the y-intercept. It would be a different y-intercept. The only way that you can have no solution with two linear equations is if they're parallel. Same slope, different y-intercept. What would happen, separate question here, what would happen if the numbers were the same on both sides after the variables canceled out? Infinitely many solutions, which would mean what about the two lines? It'd be the same line. Yeah. So if something like this happens where your variables cancel out altogether and you get different numbers, those are parallel lines. They will never intersect. If you cancel out all the variables and it ends up being the same number on both sides, that just means we're looking at the same line and there's infinitely many solutions. All right. Example 3. This is our last substitution method. Then we're going to go on to elimination. So here we go. Apply the substitution method. Miss Washington is preparing a hydrochloric acid solution. She will need 300 milliliters of a 5% HCI solution for her class to use during the lab. If she has a 3.5% HCI solution and a 7% HCI solution, how much of each solution should she use in order to make the solution needed? So basically, she doesn't have the 5% that she needs. but she has two separate ones, one that is more concentrated at 7%, one that is less concentrated at 3.5. And if you get the right mixture of those two, you can create a 5% mixture. So we're going to have to figure out how much we need. So total amount of solution, how much does she need total? What's the volume that she needs? She needs 300 milliliters. So if we say that the 3.5% solution is X and the 7% solution is Y, if we have a certain amount of X and a certain amount of Y, we need to have a total of 300 milliliters, which is this first equation here, X plus Y equals 300. Generally speaking, if you have some sort of word problem and it has two separate scenarios and it says you need a total amount of these two things, that will be an equation of X plus Y equals whatever the total amount is, because a certain amount of 3.5% plus a certain amount of 7% has to add up to 300 milliliters because that's how much she needs. So it says, let the X amount be 3.5%, the amount of 3.5% solution, and the Y be the amount of 7% solution. Now, on the opposite end, we know that the second equation ends up needing to be a certain amount of 3.5% solution, which as a decimal is 0.035. So you take 0.035, the percentage, multiply it by however much you need of that solution, add it to the 0.07, which is 7% solution, the amount of that we need, which we don't know. That's what we're trying to figure out, how much of each of them. And that's going to equal a 5% solution totaling 300 milliliters. So percentage times amount plus percentage times amount equals percentage times amount. Everybody good with that? Okay. Now, first thing we need to do to solve is we're using substitution here, get one variable on one of the equations isolated. Now, in terms of ease here, X and Y on that first equation would be equally easy to get by itself. And it's suggesting here, get X by itself. Great, let's do that. How would we get X by itself here? Subtract Y. So X equals negative Y plus 300. Now that we have that, X is equal to negative Y plus 300. So we're going to take this X value here, and we're going to plug it in for this X value here. So we're going to get 0.035 times negative Y plus 300 plus 0.07 Y equals 15. Why is it equal to 15 now over here? Where'd that 15 come from? Yeah, 0.05 times 300. 0.05 times 300 is 15. So they just simplified, multiplied those two together to get 15. All right, now we distribute. So that's going to be negative 0.035 Y plus, what's 300 times 0.035? What is it? 10.5, exactly. Great, 10.5. All right. And then if we simplify these two things together, negative 0.035 plus 0.07 is positive 0.035 Y. And then if we subtract 10.5 from each side, 15 minus 10.5 is 4.5 right there. So two things happen. Like terms were combined to equal this. 10.5 was subtracted from both sides to equal 4.5. Then we're going to divide. 4.5 divided by 0.035 should end up being a much larger number than 4.5. So what is it? Roughly. Give me to the nearest hundredth. Yeah, 128.57. All right. So we need about 128.57 milliliters of the 7% solution. That's what we're saying there. And so if we need a total of 300 milliliters, we could just subtract that from 300 then. to get the amount of 3.5% solution. So 171.43 is what that would be. And over here, it substitutes back in and does the math for us, which is fine. Although I would recommend using the x equals negative y plus 300, because then you can say x is equal to negative 128.57 plus 300, which then means that x is approximately 171.43. So for the solution here, the solution for the solution of the system is about 171.43, 128.57. Make sure your x and y go in the right spots, right? We solve for y first, but it still goes in the y coordinate position in the point on the graph, and then the x goes first. So Miss Washington should use 171.43 milliliters of 3.5% solution and 128.57 milliliters of the 7% solution. Cool. Questions on that? So everything we've done so far, substitution. Now, let's transition over to elimination. The reason why there is another method for solving systems using algebra is because depending on how the equations or the systems are written in the first place, sometimes it's just a little bit easier to use one of these two versions versus the other. Elimination is usually a lot more handy to use when your equations are both in standard form. So I'll show you that in a second here. You might remember this already as well. Systems of equations may be solved algebraically using elimination, which is the process of using addition or subtraction to eliminate a variable. This is where you combine both equations all the way through once you have them lined up. So you need to make sure that you line up everything first. So I don't know why it doesn't say that on here, but you need to line up your x's, your y's, and your regular values. So make sure they are aligned. And then once you do that, sometimes you need to do step one. You don't always. A lot of times you do. Multiply one or both of the equations by a number to result in two equations that contain either opposite or equal terms. We'll talk about that when we get there. Then you're going to either add or subtract both equations fully together. And when you do that, one of the variables is going to be eliminated, leaving you with only one variable. So the whole idea is to, with substitution, is to create one variable to solve for. With elimination, same idea. Create one variable to solve for. Then you're going to solve the equation for whatever variable you have left. Once you have that, you're going to take that value and plug it back into one of the two original equations and solve for the other variable. So it's actually a really similar process, especially once you get to step 3. So if we look at these two equations here, are the x's lined up on top of each other? Yeah. Are the y's lined up on top of each other? Yeah. Are the regular numbers on the other side lined up on top of each other? Yeah. So everything's lined up. That's what I mean by lined up. X is lined up, Y is lined up, regular numbers lined up. These are both nearly in standard form, X, Y, regular number. The first values aren't positive, so they can't really be standard form, but it doesn't really matter if they are or aren't, as long as things are lined up. And then step 1 says to multiply one or both of the equations by a number to result in two equations that contain opposite or equal terms. Do any of these terms have either opposite or equal values? Which ones? The y's. Yeah, the y's are equal values. They're -9. So we don't need to do any multiplication here. We don't need to make any adjustments to these two equations because they already both have the same number here. And this one tells you, now I don't really understand why it's doing this when it already told you that you can have the same or opposite values. I mean, I know why they're doing it, but I'll show you what they're talking about anyway. You don't have to do this step, first of all. This step here is not entirely necessary. You can. So it says multiply the second equation by -1 to get opposite terms, -9y and +9y. So if we do that, that's going to be positive 4x plus 9y equals 23. Now, the reason why they did that is because if this is a -9 and that's a +9, to eliminate them, you would add the two equations together. That's why there's a plus there. I'm going to show you the other method in just a second. -2 plus 4 is 2, so that's 2x. -9 plus 9 cancels out. And then -25 plus 23 is -2. And if you divide both sides by 2, that means that x is equal to -1 because -2 divided by 2 is -1. So add the equations together. One of the variables cancels out. You're left with 1. Solve for the 1 you're left with. And then you go back and you substitute this value into either one of the original equations. It does not matter which of the two originals you substituted in for. It's plugging it in for the second equation. That's fine. So -1 substitutes in for x. -4 times -1 is 4. So that's going to be 4 minus 9y equals -23. I'm just going to fill that in there because they're taking away the 4 from both sides. So that'll be -9y. -23 minus 4 is -27. And if you divide -27 by -9, you get 3. So the x value is -1 and the y value is 3. That's our answer. Now, in terms of multiplying that second equation by -1 or the first equation by -1, that was not entirely necessary. We did not have to do that. So go ahead and fill this in, and I'm going to show you the other way where we can avoid that first step. Because as long as you have the same value with either x or y, you can eliminate right away. So I'm going to use the margin over here. I'm going to rewrite both equations. -2x minus 9y equals -25. And then -4x minus 9y equals -23. Now, if you want to, you are more than welcome to make sure you have opposite values for either x or y. There's no problem with that. But even if you have the same number in front of x or y, you can eliminate right away. It's just that you wouldn't be adding the two equations together. You'd be doing what? You'd subtract them. So you'd subtract both of those equations. And you'll get the same answer either way. Because if you take -2 and you subtract -4, -2 minus -4 would be -2 plus 4, which is 2. That's 2x. -9 minus -9 would be -9 plus 9, which cancels. If you subtract the same number from itself, it will cancel out. And if you take -25 and you subtract -23, subtracting a negative is adding. -25 plus 23 is -2. And if you divide both sides by 2, you get x equals -1. Same answer. And then you'd plug back in and solve for y, which we already did. So I'm not going to go through that process again. But if you have the exact same number, you can subtract both of the equations. If you would prefer having opposite numbers, that's fine. That means you can just add them every time. So if you want a consistent way of doing it, make sure you have opposite values and you can just add the equations together. If you don't care if you're adding or subtracting, as long as you recognize you either have opposite or exact values for x or y, you're good to go. Questions on that? Couple more quick examples on the next page, and then we are done. Here we go. Example 5, use elimination. So on this one, x's are lined up, that's good. Y's are lined up, that's good. Regular numbers are lined up, also good. So if you see problems that are written like this, elimination is going to be your best bet. However, 2 and 3, not the same number, not opposite numbers. 5 and -4, not the same number, not opposite numbers either. So we have to make sure that we multiply either one or both equations in order to get the same or opposite values in front of either x or y. So, for example, we could multiply the first equation by 3 and the second equation by 2 in order to get 6 in front of the x's. Then we could subtract. Or you could multiply the top equation by 4 and the bottom equation by 5 to get positive and -20 in front of the y's, and then you would add them together. It doesn't actually matter how you do this as long as you get the same or opposite values in front of x or y. Now, it looks to me like they're going with the idea of getting 6 in front of the x. Multiply equation 1 by 3, multiply equation 2 by 2. So if you multiply the first equation by 3 and the second one by 2, that will give us a 6 in front of the x's. Don't forget to multiply everything in both equations by those values, though. That is important, but the whole purpose is to get the same number in front of x. So if we multiply the first equation by 3 and you distribute the 3, you're going to get 6x plus 15y. And then if you multiply 1 by 3, you get 3. So 6x plus 15y equals 3. On the second equation, multiply this one by 2 because we want to get 6 in front of the x. So 2 times 3x is 6x. 2 times -4y is -8y. And then negative 10 times 2 is negative 20, which we're allowed to do. We can do anything we want to with an equation as long as we do the same thing to both sides, which we've done here and here. So then we can line them up again, but this time we're lining them up with the same value in front of x. And so we're going to subtract both of these equations all the way through. 6x minus 6x, gone. 15 minus negative 8 is the same as 15 plus 8. What's 15 plus 8? 23. So 23y. And then 3 minus negative 20 would be 3 plus 20, which is 23. 23 divided by 23 is 1. So y equals 1. And then substitute into either one of the two original equations. They're going with the first one, 2x plus 5y equals 1. So if we use that very first equation, substitute in 1 for y, that'd be 2x plus 5 times 1, which is 5. 2x plus 5 equals 1, which would then be 2x equals 4, because you'd negative 4, because you would subtract 5 from both sides. What's negative 4 divided by 2? Negative 2. So x is negative 2, y is 1. So sometimes it's necessary to multiply one equation. Sometimes it's necessary to multiply both. Let's have a look at this very last one, and we'll call it a day. Perfect timing. Okay. Tomorrow, the 20 minutes we have for class tomorrow will be work time. So you can work on whatever you need to during class tomorrow. So here we go. Use elimination. X's are lined up, Y's are lined up, regular numbers are lined up. We want to get the same number in front of either X or same or opposite numbers in front of either X's or Y's. So what would be the best thing to do here to make that happen? Oh, I guess we could divide. I don't usually think of dividing an equation by 3, mostly because multiplying guarantees, for the most part, that we're going to get whole numbers. Well, you could divide the top one by 3. There is no problem with that. However, if you divide 14 by 3, you're going to get 14 thirds, which is not the most happy number to work with. So if you want to do that, you're more than welcome to. If I was doing this, I would actually do what the book is saying, and to multiply, I would actually just multiply it by 3 instead of negative 3, but they're suggesting to multiply by negative 3 to get opposite values for X. But it also gives you opposite values for Y. So something strange happens here. So if you multiply the bottom equation by negative 3 times negative 3, we get negative 3 times 6x, which is negative 18x. We get negative 3 times 7y, which is minus 21y, or negative 21y. And then on the right side, we get 2 times negative 3, which is negative 6. And if you add together those two, we're adding them this time because they're opposite values. If they're the same, we subtract them, like on example 3 or example 5. Example 6, they're opposite values, so we're going to add them. Negative 18 plus 18 cancels. Negative 21 plus 21 cancels. So we have nothing on the left, 0. And 14 plus negative 6 is 8. And because of that, those aren't the same. That means there's no solution. If the variables canceled out and we got the same number on both sides, that would indicate infinitely many. So once again, those two equations are parallel. That's all I got for you for the notes reading. So your assignment is going to be the same as what we saw yesterday.